going to take a look at electron configurations for the fourth period and below. We're still going to follow the Aufbau principle, which states that electrons will always be placed in the lowest available orbitals energy-wise, and we know that there's a maximum of 2 electrons per orbital. However, subshells do not increase in energy in an obvious way after 3p. So we know that the lowest energy orbital is always 1s, and then comes 2s, and then 2p, and then 3s, and then 3p. We would expect 3d to come next, but that's actually not the case. 4s is actually lower in energy than 3d. After the 3p subshell, the subsequent or the higher energy orbitals and subshells are much closer in energy to one another, and they don't follow a really obvious order. So for example, the 4s is lower in energy than the 3d. Now within a given principal quantum number, the s subshell will always be lower in energy than the p subshell, which will always be lower in energy than the d subshell, which will always be lower in energy than the f subshell. However, there will be some mixing of energy levels. As we see here, the 4s is lower in energy than the 3d. So how are we going to keep track of that? Well, one way is we can devise this diagram, and this diagram is very easy to replicate. To draw this diagram, number 1 through 7 on this far left hand corner, and these represent the 7 periods of the periodic table. And then we'll have 4 columns representing the subshells in energetic order: S, P, D, and F. Now in our first energy level, we have only the S subshell allowed, and every energy level that's higher also has an S subshell. So we'll write 1s, 2s, 3s, 4s, 5s, 6s, and 7s. The next column is the P subshell. That becomes allowed at the second energy level. So we'll write 2p, 3p, 4p, 5p, 6p, and 7p. The next column is the D subshell, which becomes allowed at the third energy level. So 3d, 4d, 5d, 6d, 7d. And the last subshell is the F, which becomes allowed in the fourth energy level. So 4f, 5f, 6f, 7f. So this diagram is very easy to construct, and the way that we use it is that we place electrons in each subshell, 2 per s, 6 per p, 10 per d, and 14 for f, in this order. We start with 1s and follow diagonal arrows, and we fill each subshell before going to the next subshell, and then once we get to the S subshell, we go to the next arrow below the end of the arrow and follow the diagonal, filling subshells before we go to the next subshell. Here's the order down here that we would get by following this diagonal: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, etc. Alright, so let's use this diagram to write the electron configuration for arsenic. So the first thing we need to do is find arsenic on the periodic table, and we see it has 33 electrons. So what I'm going to do is I'm going to start to arrange these 33 electrons according to this chart. So 2 electrons can fit in my 1s. So I'll go ahead and write that down. 31 more to go. Next I go to my 2s, and 2 electrons can fit. After the 2s I go to the 2p. 6 electrons can fit in that subshell. And then after the 2p, the 3s, where 2 electrons can fit. After the 3s, I now go to the 3p, where 6 electrons can fit. And if I count, I have 18 electrons. Okay, so I still have more to go. After the 3s, oops, this is not 3s, this is 3p. Okay, after the 3p, now I go to the 4s. And now I have 20 electrons. Okay, so 13 more to go. So after the 4s, I'm going to go to 3d, which can take 10. And now I just have 3 more to go. So after the 3d, I go to the 4p, and that's where my last 3 electrons will go. So now I have my electron configuration for arsenic. Here it is. All 33 electrons are accounted for. And by using this chart, I was able to place the electrons in the lowest available energy, or the orbitals that had the lowest energy, which is following the Aufbau principle.